Welcome everybody to example 2. We are still looking at page 125 in the workbook here. And this is an example where we're just going to try to prove a couple of basic properties of the complex numbers. If this were a complex analysis class, you would probably go into a lot more detail and prove a lot more things about complex numbers. We're just going to talk about the basic properties that we need for this course. Okay, so let's start with part A here. What is this asking us to prove? Well, it's basically asking us to prove that the conjugate of a product is equal to the product of the conjugates. It seems like a thing that should reasonably be true. We just want to prove that it's always going to be true for any two complex numbers. Okay, so since we'd like this to be true for arbitrary numbers, how about if we start by picking ourselves a couple of arbitrary complex numbers? So we'll let z1 be a plus bi, and z2 be c plus di. We know that every complex number has to have that standard form. Okay, well, we're trying to prove that an equation is true, and so the strategy that I'd like to use is to kind of work with one side of the equation at a time. Let's start with the left-hand side of the equation, z1, z2 bar. Okay, well, by our choices of z1 and z2, this would look like a plus bi times c plus di with a big bar over it. Okay, so we can do some algebra here. And if we actually expand the a plus bi times c plus di, that works out to be ac plus, add the middle terms, that's going to give us bci plus adi, and then finally b di squared. There's a big bar over all of that. Okay, can we simplify that at all? Well, let's see. There are two terms that have i's in them, so we could combine those together. Maybe write it as bc plus ad times I. And then we come to bdi squared, and remember that I squared is really -1. So this is really minus bd. Okay, we've still got that bar over the top. Okay, so organizing this into its real and imaginary parts, we can write the AC minus the BD together. Those are both real portions. And then the BC plus AD, I at the end. Okay, well, what's left to do here? Really, the only thing that we haven't processed yet is the big bar over the top, which means, again, the conjugate of this entire complex number. What was the conjugate of a complex number? Well, it was just the new number that we get by changing the sign on the imaginary part. So the conjugate of this would just look like AC minus BD minus BC plus ADI. We just changed that sign here that we circled. Okay, so this is the result of the left-hand side of our equation, z1, z2 bar. Okay, what about the other side of the equation? Well, the other side of the equation looks like z1 bar, z2 bar. What we're hoping is that if we do that calculation, we get the same thing that we did above. Okay, so how would that look? Well, let's see. z1 is a plus bi, bar over it, and z2 is c plus di, bar over it. Okay, if we do that calculation, we're doing the two conjugates separately, so we're going to get a minus bi times c minus di, and then we have to do the multiplication. So let's see, we're going to get an AC, our two middle terms this time are going to look like minus BCI minus ADI, and then plus BDI squared. Okay, simplifying again, we can put some terms together. So let's see, what do we get here? Hang on a second here. Okay, maybe a better way to write this would be AC minus BC plus ADI, and then noticing that BDI squared is minus BD. Okay, and if we put everything back together, let's see, kind of group like terms together, we're going to get AC minus BD. There's the real portion. minus BC plus ADI. Okay, but look at what we've got here. We calculated Z1, Z2 bar, and we got this. And we calculated Z1 bar, Z2 bar, and we got exactly the same thing. So we have just confirmed that the right and the left-hand side are the same. Okay, and there's our proof of part A. Okay, so if you'd like to pause the video now and try part B on your own, feel free to do that. Okay, take a minute, and we'll come back and do part B together. Okay, welcome back. We're going to take a look at part B now. Okay, and this is kind of the same thing. I'm going to just scroll up here so we can see that question before we dive into this. Okay, this is asking us to prove that the modulus of a complex number z is equal to the square root of the product of z with its conjugate, basically. We'll approach this the same way that we did part A. Okay, so we're starting with an arbitrary complex number, so let's let z be a plus bi. And we'll work with one side of that equation at a time, starting with the left-hand side. Okay, so how is the modulus of z defined? Well, it's the square root of a squared plus b squared. That's the same definition that we wrote at the top of this page. What about the right-hand side of the equation? Well, that looks like the square root of z times z bar. We can do the algebra and just see what that looks like. So let's see, that would be the square root of z, which is a plus bi, times z bar, which is a minus bi. Okay, do a little algebra here, and we're going to get a squared. The middle terms are going to look like a plus abi and a minus abi. And then we get a minus b squared I squared, it looks like. Okay, what happens with all of that? Well, you might notice one very nice thing that happened. These two terms cancel out. And then, so we've got a square root of a squared, and then a minus b squared I squared. There's that I squared again, which is negative 1. So that's going to turn that minus b squared into a plus b squared. And again, look at what we've got here. The modulus of z was the square root of a squared plus b squared, and the square root of z bar was exactly the same thing. And so, because those are equal, we have shown exactly what we wanted to show. Okay, and we are done. And as we proceed with this chapter, we will see that we'll wind up using some of these basic properties of complex numbers in the work that we do.